Okay. So here, in chapter 24, we have two samples. And based on what we see in our two samples, we want to know, do the two populations have different means? Okay, so we have sample 1. So for example, silly example, sample 1 and sample 2, maybe sample 1 is men, and we measure, we're looking at the heights of men, and sample 2 is women, and we look at their heights as well. And if we take two random samples, a random sample of men and a random sample of women, measure their heights, based on what we see in the sample, does that indicate to us that the populations have different mean heights? So sample 1 has come from the population of all males, of all men, Okay. And so based on what we see in our samples, that the populations Okay, so in this case, we know that the mean height for the population of men is different than the mean height of the population of women. Okay, this should not be a surprise to anybody, but we know that the average height of a male is taller than the average height of a female adult. Okay. Well, but let's say we were an alien. Okay, we've come to Earth. We're observing people, and we want to know, oh, well, I don't even know if aliens have genders or whatever, but they say, oh, well, there's the, let's say they understood at least genders. So they said, okay, well, it seems like, you know, are the males different from the females? And we're making observations here, okay? So we randomly abducted 10 males, okay? So we have a random sample of n equals 10 males, or 10 men. Is there a, what's the difference between a male and a man? I know there's a difference, but I'm never quite sure. Okay, and let's say we have 12 females. Okay, random sample. And we measure the height, okay? So to indicate that this is sample 1, I'm going to just put a subscript of 1 next to these. So average height of these 10 males, let's say, is 69.5 inches. And average height of the 12 females, let's say, is 64 inches. And the standard deviation of these 10 males, we'll say, is 2.8 inches. And the standard deviation of these 12 females, we'll say, is 3.0 inches. So based on what we see in the samples, do we have evidence that the populations have different means? Okay, so in this case, we would set up our null hypothesis would be that the two means are equal. That the mean height of population 1, in this case the mean height of males, is the same as the mean height of females. An alternate formulation would be to say that the difference in mean heights is 0. They're saying the same thing. You might see them written in either form. So as aliens from another world who've never encountered human males and females before, we might not know whether to expect the females to be larger or the males to be larger or taller. Okay? Because in insects, generally females are larger. For mammals, it seems that in general males are often larger, but generally speaking, I'm always amazed. So our alternative hypothesis, because we're not anticipating one to be larger than the other, we will use a not equal sign. Okay? But if prior to our study we had an inkling that one group would be larger than the other group, we might set the alternative hypothesis to be a greater than sign or not less than sign or something. Okay, so in this case, our test statistic our t is going to be equal to the observed difference that we see from our data. Y bar 1 minus Y bar 2. We may or may not stick in a minus 0 here to indicate that we're expecting a difference of 0 if the null hypothesis is true. Okay? So if the null hypothesis is true, we would expect Y bar 1 minus Y bar 2 to be equal to each other, or we would have a difference of 0. But adding or subtracting 0 doesn't affect our number, so we can leave this out, or you can put it in there if you want. Okay? That part doesn't matter. And then just like everything else, we divide by our standard error. Okay. The only unfortunate thing is that our standard error formula is ugly. But not too horrible. Okay, so we have the numbers from our data. And we can do this. So our test statistic is going to be 69.5 minus 64 divided by our standard error. Our standard error is going to be the square root 2.8 squared over 10 plus 3.0 squared over 12. And I'm getting a standard error of 1.239. Sure. So that goes in up here. And so my test statistic ends up being 4.44. Okay, so at this point, we would look up our test statistic in our t-table. But in order to use the t-table, we need to know the degrees of freedom. Okay. This is the unfortunate part, or the other unfortunate part of this, is that there is a formula to calculate the degrees of freedom, but it is, I wouldn't say unnecessary, it's unfortunately complicated and ugly, and to be honest, it's not that big of a deal. So, instead of trying to get the exact degrees of freedom, which is easy to do if you have a computer that can calculate it for you, but if you had to do it by hand, we're not going to use the exact degrees of freedom. We're going to just do an approximation. And depending on which textbook you use, they might say use this as an approximation or use this as an approximation. There's different, different things, okay? So for our class, we will say that the approximation that we will use, what does our textbook say? Okay, I'm just going to say for our class, we will say use n1 plus n2 minus 2 as approximate degrees of freedom. This generally overestimates the degrees of freedom, but it's usually not too much of a problem. Alright, so in this case, our approximate degrees of freedom that might be overestimated would be what? 20 degrees of freedom. Okay, so we would do df is 10 plus 12 minus 2. We would have approximately 20 degrees of freedom, and we would use that to look up our test statistic of 4.44. So you go to the back of the table, and you're not going to get an exact p-value. When I post solutions to chapters, I have to do it for 23, 24, and 25 now. When I post solutions for these, some of the solutions are going to have exact p-values, okay? But when you're using the t-table, you're not going to get exact values. You're just going to say, my test statistic ended up between these two columns, so all I can say is that my p-value or tail area is between these two column headings as well. So we would look this up. We would see that 4.44 is quite far from the quite far from 0, and we would say with 20 degrees of freedom, test statistic of 4.44 is farther away than the largest number listed there, 2.845. Okay, so in the t-table, largest critical value listed for df equal to 20 is 2.845. 4.44 is farther away than 2.845. So our two-tail probability is less than 0.01. So in this case, our data would provide evidence to reject the null hypothesis. Okay. So our tail probability is less than 0.01. So we'd say our p-value is less than 0.01, which would indicate that our p-value is small. Or our p-value is less than whatever alpha we choose, assuming even if alpha were 0.01, our p-value is less than that. We would reject the null hypothesis. We have evidence that there is a difference between the mean height of males and the mean height of females. Okay, I think we'll end there as covering hypothesis tests in chapter 24, and then hypothesis tests for paired data in chapter 25. I haven't picked out the homework problems, so I'll do that right now, and we'll come back on Monday and revisit some of the finer points from chapter 24.